Is it started recording?
Yep.
Okay. So hi everyone. My name is Kimbo. I work at Semi-Analysis as an engineer. Today I'm going to talk about the evolution of NVIDIA Tensor cores. Uh, I believe it's people say CUDA mode. I believe tensor cores are one of the most important part of the CUDA mode, so I called it the dragon in the CUDA mode. So why should we care about the evolution of tensor cores? The reason is that tensor cores are mysterious and important. As we all know, NVIDIA GPUs are one of the most important deep learning hardware accelerators that has driven major innovations in AI. As you can see in the graph on the right, uh, throughout the past almost 10 years, the NVIDIA's GPU's flops throughput has increased by quite a lot. For example, like the GB300 is closing to 15,000 teraflops at FP4. Uh, but as tensor core architecture becomes more and more complex, it is difficult for ML practitioners to keep up with the latest changes and the reason behind those architectural changes. So to the practitioners, tensor cores kind of became a mysterious black box when using them. But I believe understanding tensor cores is important because how critical tensor cores are to performance. Um, as we see in the graph on the left, which is the breakdown of the throughput by GPU, we see tensor cores compute flops are basically most of the whole GPU. For example, for B200s, it's over 90% are coming from tensor cores. It's important to understand how they work and to use them properly to squeeze the most performance out of NVIDIA GPUs. And that's the reason why we wrote the article. And today's talk, it'll be an excerpt of the talk of the post. We will be only talking about four things. First, we'll talk about at a very high level how tensor cores perform matrix multiplication, and later three design trends and the principles behind them. So first, how does tensor core perform a matrix multiplication? So before we started, we talked about this. I hope everyone has a very basic understanding or like heard of the terminologies of CUDA programming model. Here is a very summary of the terminology we'll be using. So the column on the left are the execution unit hierarchies, a thread, a CTA, and a grid. The column on the right are the corresponding memory pools. So for example, a thread can access a register file, a CTA can access shared memory, a grid access global memory. So the first thing we will talk about is how the first three generations of tensor cores, Volta, Turing, and then Ampere, how those architectures perform matrix multiplication. So there are four steps. First, you load the data from global memory to shared memory, and then you load data from the shared memory to register file. Third step, you execute an MMA operation, and then you perform the epilogue operations. Usually they refer to non-tensor core operations or operations done on CUDA cores. Um, one of the most common ones being element-wise operations or like activation functions, etc. One thing to note about those steps are it is a collective operation, meaning that it takes multiple threads to collaboratively complete the operations. It also means that it'll need some sort of synchronization, um, which we draw here in the graph. The core instruction, MMA, stands for matrix multiply and accumulate. It is a PTX instruction for tensor cores, which we will talk a bit more about later. Throughout volta to ampere, Turing is kind of in the middle between volta and ampere in terms of design. So the major differences between volta and ampere are the number of threads you need to launch an MMA. Specifically, volta uses 8 threads. Ampere uses a warp of 32 threads. The second difference is Ampere is able to load data from global memory to shared memory in an asynchronous fashion. Asynchronous execution is a very important trend or a very important feature for NVIDIA GPUs that we will see a lot more later. And we'll also explain what it does or why it exists later in the talk. Okay, so before we go further, just want to make sure uh, if everyone is following, because this is like a very rough overview. Does anyone have any maybe questions? Um, Everyone good? Okay. Oh, someone is, how do I
You,
pronounce your name? Sorry, go on, please.
yeah, you can unmute yourself, yes, if you have a question. Oh, I'm assuming maybe it's by mistake. You can go ahead, Kim. Okay.
Oh, should I go on then?
Yeah, probably, yeah.
Okay.
I
Yeah,
later.
yeah, feel free to ask questions later because I know this might be a very big jump in terms of like loading a lot of concepts and terminologies into it. Okay, so those are the first three architectures. The architecture after that is Hopper. Hopper comes with a new type of MMA instruction called WGMMA. WG stands for warp group. Warp group is basically a set of 4 warps, and which is 128 threads. By having more threads, you could use more registers, basically. The another critical feature about WGMMA is that it is asynchronous. Again, asynchronous would come up again and again, and we would talk about it later. In the matrix multiplication flow, another new component is the tensor memory accelerator, also known as TMA. TMA is a dedicated hardware unit for handling, for accelerating the memory loads from global memory to shared memory. What it does specifically is that it handles address generation, which is typically done by threads and CUDA cores. So by using a dedicated hardware unit to do so, you could free up the threads to do other operations, um, launches, epilogues, etc. Another feature is that TMAs has single thread semantics, meaning that you only need one thread to launch an instruction to get TMA to work. This is a departure from the CUDA programming model where you need multiple threads to operate. And this is also a common theme that we would keep seeing after this. So after Hopper, we get Blackwell, currently the newest architecture. The corresponding new MMA is usually called UMMA, also known as TC Gen 05 MMA. Again, it has single thread semantics like TMA. It's a departure from a CUDA programming model. And another big difference is that TC Gen 05 MMA can use two SMs to perform one single MMA. So before Blackwell, each tensor cores exist on one SM, and you launch an MMA within the SM. But now you could expand across SMs to perform even larger matrix multiplication. Another big difference in the black hole architecture is the tensor memory, also known as TMEM. TMEM is a memory component within an SM that is dedicated for tensor core operations. It replaces register files as an operand location. And one of these features is that it has a restricted memory access pattern. Specifically, in order to access the whole TMEM, you need 4 warps to do so. And every warp can only access a specific region of it. By doing so, in terms of hardware, you could reduce the number of memory ports. You could simplify the memory design, which saves power and chip area. As a result, improving the power efficiency. Another important feature of TMEM is that, again, a departure from the CUDA programming model, where each thread holds a specific set of registers. TMEM's memory can be accessible across different warps, meaning that I can use one warp to load data into TMEM, but later use another warp to store data from TMEM. By having this, we can simplify some advanced features in Blackwell, such as warp specialization. And by doing so, you don't need the ping pong scheduling in Hopper and have a simplified workflow. Ping pong scheduling and warp specialization are quite complicated features and techniques. I don't think it's even covered in the blog post, but for people who are interested, I would recommend watching the Blackwell GTC Cutlass talk. They talk about the pattern. Okay, so the first trend I want to talk about is the fact that tensor core size is increasing generation by generation, and the reason why, and also the principle behind it. So tensor cores have been able to perform increasingly large matrix multiplications. This implies that the tensor core size is increasing. The graph on the right shows the number of flops that you need to perform the major MMA shapes for each GPU. So we see the y-axis is actually a log in log format, meaning that the number of flops is actually increasing exponentially. So the motivation behind performing, like making tensor cores performing larger macros is because matrix multiplication has a linear arithmetic intensity. Specifically, we all know matrix multiplication is cubic in computation, but it's also quadratic in memory loads. So arithmetic intensity being computation over the number of bytes loaded, having a linear arithmetic intensity, meaning there will be, arithmetic intensity scales linearly with the size of the matrix multiplication. And having a higher arithmetic intensity implies that there will be a higher performance ceiling. Because of larger MMA shapes, it is also why we need to increase the thread count to launch the MMA, at least before Blackwell. So we see in Volta uses 8, Ampere uses 32, and Hopper uses 128. By using more threads, you could allocate more registers, um, and you could load larger MMA shapes. You could improve the data reuse, increase the data reuse by because you don't need to reload parts of or tiles of the same matrix by just loading everything once. The reason why architecture designers are so conscious of memory loads is because in the blog post we call data movement is a sin, because so the reason why it's a sin is because um, memory speed and memory capacity hasn't been improving as fast as compute. So making computation a lot cheaper than data movement. So that's why Tensor Core architecture designers are very conscious of how much data movement you need to perform matrix multiplication and to get good performance. The second trend I want to talk about is the programming model going to low occupancy and even single occupancy. And the principle behind it is strong scaling. So for non-deep learning CUDA programming, we usually do a thing called oversubscription. This means that we programmers try to allocate multiple work units and designate them to the workers so that each worker has multiple work units to work at the same time. And while by context switching between multiple work units, a worker can save time when one working unit is stalling, it can switch to the other to do work. This type of concurrency is, or this kind of parallelism is what GPUs do. And programmers usually measure this kind of parallelism in terms of the number of active workers. In PTX machine model in NVIDIA, we measure a number of warps. So this is also called occupancy. So in non-deep learning CUDA programming, having a high occupancy is the key to performance. However, in deep learning CUDA programming, NVIDIA GPUs strive for low occupancy and even single occupancy. A way to understand why this is happening is that for the same matrix size, as we see in the graph here, if we increase the MMA shape, like we saw in the first trend, we will have less working units because MMA shapes are getting larger. So since there are less working units, NVIDIA designed it so that the number of working units, each worker is assigned one working unit. And actually, in some cases, even one single unit would use multiple workers. So why did NVIDIA try to change to low occupancy and single occupancy? The reason is NVIDIA wants to strong scale matrix multiplication. So strong scaling and the opposite, weak scaling, they have definitions. Please refer to the blog post or search up on what they mean. But what I want to talk about is the effects of strong scaling and weak scaling. The effects of strong scaling is that it improves the performance across all problem sizes. In our case, it'll be improving the performance of all matrix shapes, while weak scaling the opposite case would be adding more tensor cores. This way, it only guarantees better performance on larger matrix shapes because you need more working units to saturate more workers to improve performance. But that doesn't guarantee for the same matrix shape, it will run faster. Okay. The last feature is the asynchronous execution, and the principle behind it is Amdahl's law. So the reason why we need asynchronous execution is because strong scaling matrix multiplication almost requires asynchronous execution. One way to see this is that if we draw the matrix multiplication flow, as we see here in the graph, LDGSDS, the red boxes are basically data loading, and the green boxes are the MMA operations. So if we try to improve our strong scale MMA, in this case, Tensor Core's throughput has been doubling very fast. The dark green boxes, they have shrinked by quite a lot. But as we do so, data loading would become a bottleneck very quickly. And this is quantitatively described by Amdahl's law. Amdahl's law, please look it up. There's like formulas for it. But the idea is that scaling, strong scaling specific components would make other things the bottleneck, and no matter how fast you scale specific components. The way to avoid Amdahl's law or work around Amdahl's law is by introducing asynchronous execution. So you overlap the data loading with the MMA operations that we see in the third row. So by being able to overlap them, you could avoid the bottleneck of data loading. Asynchronous execution has been a trend in the NVIDIA's architectures. Every generation comes with new asynchronous features, which we don't have enough time to go through every of them. But if you're interested, please read the blog post. This is like a summary of the tables, a table of the main features that are asynchronous. Okay, so that's pretty much what the four main things. Finally, I want to talk about what is semi-analysis. So semi-analysis is a research company that offers insights into the AI industry, starting from data centers all the way down to semiconductors. We create benchmarks and analyses like the post that we were talking about, the Tensor Core evolution posts. And in addition to architectures, we also do across different sectors. Personally, my focus is ML systems, and my Twitter and Discord handle are both Kimbo Chen. Feel free to contact me. And finally, I just want to shout out to my favorite cover image, which is the one you see here. It's drawn by Simon Guo. Okay. Thank you everyone for listening, and I'm happy to answer any questions.
If anyone has a question, you can just probably unmute and go for it. Does anyone want to go first? Okay, cool. Probably I could ask a question. I
Yeah,
think
sure.
one slightly like this is my understanding that from Hopper at least a lot of the benefits, or this, I mean, like, to use a naive term, the speed up or the flops, right? It seems to be coming from architectural changes like the TMA and other like the WG MMA that's on Hopper,
Mm-hmm.
and the other GPUs don't really have it, right? Like, so for example, in the ADA generation, the L40S, for example, it just doesn't have this. And then moving forward, like a concerning trend is that a lot of the performance is going to be limited to like the topmost line of GPUs. Do you also get that sense from your research, like, or where are the other GPUs going to, like, are they going to be permanently bottlenecked in some sense, like, not what is not the B200, what is not the H100, say the ADA 6000 or the L40S, or does that broadly make sense, the question?
Yeah. So my to repeat what you said, my understanding is you're asking about um, whether these features that we saw in the talk is whether they exist in only just top of the line data center GPUs or not.
I'd
Is that
assume that
what you're trying
they
to say?
I'd assume they don't exist, right? Like, because since the hardware is not there on the other GPUs. So
Yeah. So I think I'm not sure for every feature, like either they exist or not. One thing I'm certain is that the features that I mentioned here all exist in the data center ones, and the other thing is that for MMA, this um, MMA has always existed across different architectures. Or at least MMA still exists in Hopper and Blackwell, but it's just not, it doesn't make sense to use them given that they're not as performant. And MMA, if I remember correctly, exists on consumer GPUs, even for the Blackwell ones. And that is the one that is used on the consumer GPUs. Does that make sense?
yeah, so we like is the curiosity was more like, do you see like some other line of optimization for like the non high end data center GPUs? I'm just curious because this was a bottleneck. So yeah, that was broadly, but I get what you're saying in terms of like you would just use a different set of operations on you'd use the MMA if you don't have access to an H100 or say a Blackwell or something of this sort. Yeah.
Yeah, I don't know the details of the architecture differences. I know typically they do um, um, like even within between chips, the same H100s, um, they different versions of H100s, they disable a number of SMs depending on the version you get. So I think it's quite common that um, chips have different feature sets being enabled. Um, but yeah, I don't know the exact um, what features exist in what line of GPUs.
I think there was a question in chat. I'll just probably read it out. Unless Srihari, do you want to unmute and speak? Okay, you can. No worries.
Um, okay, so I see a question. So a sense of timeline of this evolution. Yeah, yeah. So Volta started in 2017, um, Turing 2018, Ampere 2019, and Hopper. Yeah. I don't know. I don't remember top of my head for the numbers, but I think Hopper is around the 2020s, either 2020 or 2022. I don't know, remember exactly. And then it comes Blackwell. Blackwell is the latest, at least for now. Um, uh, B200, the number that we're referring to, is one of them, and the upcoming one being, I think, the GB300s. Okay, second question. What are some research areas that have the potential to create another generation? Um, I'm not sure what you mean by this question. If you can clarify a bit, that'd be great.
I mean, I could try to provide some more detail. Like I saw, from what I could understand, it seems like asynchronous computing at the chip level is that's like one of the breakthroughs in enabling the latest generation. Is there something like that that's being researched? I'm sure there's like a variety of things, but do we have like a sense of some promising areas that could prompt yet another revolution?
I think I roughly get what you mean. I think in terms of I wouldn't say asynchronous execution being like an like research area. It's more like a principle that applied that the designers applied. So it has always been there. It's just a matter of how much or how you apply them. But one thing I would guess is another trend is we talked a lot about in the talk, which is uh, the the flow of matrix multiplication is departing from the CUDA programming model. So, for example, you right now you basically need only one thread to launch most instructions, and whereas in CUDA programming model, you typically do multiple threads and collaboratively do things. And there are a couple more trends mentioned in the blog post, which I took out because of we don't have enough time. Um, but yeah, feel free to read the blog post for more other trends in it. So back off the top of my head, maybe the trend is also reducing data types, which is very relevant to our efficiency group. From FP32 all the way down to FP4 recently. Um, what are the things? Yeah, things like that. Yeah, please look read the blog post. Any more questions?
I just generally as a another question, right? Like this is more of a how you put it, like a speculative question than it is a concrete one. Is programming complexity the trade-off that's coming in with programming complexity across generations? Like how we would be, is it getting significantly more to draw more performance out of these tensor cores across these things, or is it like almost simplified? Because I believe you mentioned like there were some restrictions that are coming in terms of memory access and those kind of things. Like, do you have a broad sense of how this is also trending, other than from the software side of things?
So as far as I understand, the programming complexity is Volta actually is very difficult to program properly because the Tensor Core design, like we mentioned, it uses 8 threads. But we all know the unit of execution or the programmers usually think in warps when it comes to CUDA programming model. And it being using 8 threads kind of makes the data layout very complicated. For more information, can look to the Volta Cutlass talk. They have very beautiful visualizations of how complex that layout is. But Ampere because using threads and other designs, corresponding designs, Ampere is actually very a lot better, a lot easier to program compared to Volta. And Hopper became complicated again because it's trying to use 4 warps to cross the warp concepts of CUDA programming model, and it makes calculations a lot more complex. And Blackwell actually simplifies Hopper. I heard a lot of kernel programmers tell me Blackwell is so much better designed. Um, main thing being the tmem that we mentioned. So the restriction in the memory access pattern, my guess is that, I'm not sure, but my guess is that it wouldn't be increasing the programming complexity too much. It would be just a matter of how you allocate declare the warps to load what part of the data. So does that answer your question? So maybe
Yep.
just in summary, just Volta very hard, Ampere easier, Hopper became hard again, and Blackwell became easier.
So bucking that trend, the next one might be hard again, and we have more.
By extrapolation, I don't know.
Yeah.
Hopefully not. Hopefully not.
Yeah. I think one last question, like building on what Srihari kind of asked. It seems like NVIDIA is betting huge on quantized data types, like quantized training. So they're reporting these magic numbers at every generation, like with, I think, with Hopper, they did FP8 flops, and then with
Mhm.
Blackwell, it seems to be FP4.
Mhm.
I see. I think we've had a lot of work over the past two months or so of
Mhm.
people coming in and talking about like stabilizing training and those kind of ideas, right? But
Mhm.
these are diminishing returns. I think after FP4, it becomes very dicey. You start going into like sub 4-bit is a weird situation to be in.
Mhm.
Uh, I wonder,
Yeah,
is
yeah.
it
Mhm.
is it really going to trend towards sub 4-bit? Like I know we have micro scaling and those kind of ideas, etc. But
Mhm.
like for me, it's not clear. Like the question is like, where do the next benefits come so easily? Because we can't just lop off another 2 bits and just be happy, I guess. So
Mhm.
just curious on that part.
Yeah, yeah. Very, very great question. So, uh, in terms of architecture, um, we also wrote this in more detail in the blog post, is the data type reduction trend. Um, it makes a lot of sense from the architecture perspective to reduce the precision. So in principle, you don't need uh, as many bits to do machine learning operations, and because of that, um, reducing the number of bits has uh, many performance benefits, including you use less bandwidth, you use less power to activate the less power to do the computation. You need um, less capacity. You can load more parameters at the same time, given the same amount of capacity. Many benefits. But this, like you said, uh, architecture wise, it makes sense. But the reality is that, does it impact, or how much does it impact the model capabilities? Um, So, as far as I know, right now, FP8 is the standard for training, um, and deploying FP8 is easy and intuitive, basically training what you get. Um, for the newer generations, for like Blackwell, we support like MX microscaling formats, which seems to be standardized. But one thing we highlighted in our post is the difference between um, FP4 formats, which is the NV FP4, the one that NVIDIA used and the standard MXFP4. And as far as we see, NVFP4 is far superior from MXFP4. I think the trend is definitely going downwards. We're right now stuck at FP8, and FP4 is still at the inference stage. But yeah, who knows? Maybe someone to figure out how to do training in FP4, and I would say integer formats is also a potential. So yeah, hopefully that answers your question.
Yeah, that was good. Yeah, but unfortunately, I think they lopped off the Info Tensor course. So probably they're making that decision for us, NVIDIA, in some sense. I think in Blackwell
Yeah,
doesn't have it anymore. Yeah,
yeah, hardware lottery. Yeah, basically. Yeah, yeah.
makes sense. Yeah.